Hello, and welcome to Calm Science Nights. I'm so glad you're here with me tonight. Before we begin our journey into the cosmos, if you find peace in drifting off to the soothing rhythm of scientific discovery, please consider subscribing to the channel. It helps us create more of these tranquil explorations together. Now, settle into your most comfortable position. Let the weight of your blankets feel like the gentle pull of gravity, grounding you safely to Earth as your mind prepares to wander among the stars. Feel your body sinking into the mattress like a spacecraft settling into orbit, peaceful, weightless, perfectly balanced. Allow your breathing to slow and deepen, like the patient rotation of planets around the sun. Tonight, we're going to journey beyond our world, into the vast darkness between stars, exploring the science that has allowed humanity to understand the universe and our place within it. Over the next 100 facts, we'll trace the story of space science from ancient observations to modern discoveries, told as a narrative of curiosity, wonder, and revelation. There's no need to stay awake for all of it. In fact, the greatest compliment you could give is to let sleep take you whenever it wishes, perhaps somewhere between the Earth and the Moon, drifting into dreams as we drift through the cosmos. Just allow these words to wash over you like starlight, gentle and infinite, carrying you peacefully into rest. Close your eyes now, and imagine yourself looking up at the night sky on a perfectly clear evening, far from city lights. The stars spread above you in countless thousands, the Milky Way a river of light stretching across the darkness. For most of human history, this view was the extent of our cosmic knowledge, beautiful, mysterious, but fundamentally incomprehensible. We had no idea what stars were, how far away they lay, or what laws governed their movements. Tonight, we'll follow humanity's journey from that ancient wonder to modern understanding. Our story begins not with telescopes or spacecraft, but with patient observation and careful thought. Ancient astronomers noticed something curious about the night sky. While most stars maintained fixed patterns relative to each other, forming the constellations that cultures used for navigation and storytelling, a few bright objects wandered. The Greeks called them planets, meaning wanderers. Our word planet comes from this ancient observation. 5 planets were visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. These wanderers moved against the background of fixed stars, tracing complex paths across the sky that seemed to defy simple explanation. For centuries, the dominant model of the cosmos placed Earth at the center of everything. This seemed intuitive. After all, we don't feel the Earth moving, and the sun and stars appear to circle around us daily. The geocentric model, refined by the Greek astronomer Ptolemy around 150 CE, could predict planetary positions with reasonable accuracy using a complex system of circles within circles. Planets moved on small circles called epicycles, which in turn moved on larger circles called deferents, all centered more or less on Earth. The mathematics worked, after a fashion, but the system was complicated and inelegant, requiring constant adjustments to match observations. The breakthrough came in 1543 when Polish astronomer Nicholas Copernicus published a radical proposal. The Sun, not Earth, sat at the center of the solar system. In the heliocentric model, Earth was just another planet, orbiting the Sun like all the others. This single change simplified the mathematics dramatically. The apparent wandering of planets, their occasional backward motion called retrograde, suddenly made perfect sense. It was an illusion created by Earth's own movement. When Earth, moving in its orbit, overtook a slower outer planet like Mars. That planet appeared to move backward against the stars, just as a car you're passing on the highway briefly seems to move backward relative to distant mountains. But Copernicus's model still wasn't quite right. He assumed planetary orbits were perfect circles, which required almost as many corrections as Ptolemy's geocentric system. The next crucial step came from Johannes Kepler, a German astronomer working in the early 1600s. Kepler had access to decades of precise observations made by Danish astronomer Tycho Brahe, the most accurate naked-eye astronomical measurements ever recorded. Tycho had spent years meticulously tracking planetary positions night after night, creating a dataset of unprecedented quality. Working with this treasure trove of data, Kepler made a discovery that would transform astronomy. Planetary orbits aren't circles, they're ellipses. An ellipse is an oval shape with two focal points rather than a single center. Kepler found that planets orbit the Sun in elliptical paths, with the Sun positioned at one focus of the ellipse. This was his first law of planetary motion, published in 1609, and it was revolutionary because perfect circles had been assumed to be the divine shape of celestial motion for 2,000 years. Breaking free from this assumption allowed Kepler to describe planetary orbits with perfect accuracy for the first time in human history. But Kepler didn't stop there. His second law described how planets move along their elliptical orbits. A planet moves faster when closer to the Sun and slower when farther away, in a precise mathematical relationship. If you imagine a line connecting a planet to the Sun, that line sweeps out equal areas in equal times as the planet orbits. This explained why planets speed up and slow down in their yearly journeys. It wasn't random or mysterious, but followed an exact geometric principle. Kepler's third law, published 10 years later in 1619, revealed an even deeper harmony. There's a mathematical relationship between how long a planet takes to orbit the Sun and how far away from the Sun it orbits. Specifically, the square of a planet's orbital period, the time to complete one orbit, is proportional to the cube of its average distance from the Sun. This meant that knowing how long a planet's year lasted would tell you its distance from the Sun, or vice versa. The solar system, Kepler showed, was governed by precise mathematical laws, not divine whim or arbitrary complexity. The universe was comprehensible. While Kepler was discovering these laws through mathematical analysis of planetary positions, an Italian scientist named Galileo Galilei was revolutionizing astronomy in a different way, by turning a newly invented device called the telescope toward the heavens. In 1609, Galileo heard about a Dutch invention that used glass lenses to magnify distant objects. Within months, he had built his own improved version and became the first person to systematically study the night sky with magnification. What Galileo saw through his telescope shattered ancient assumptions. The moon, which appeared smooth and perfect to the naked eye, revealed itself to be covered in mountains and craters, rough, Earth-like terrain, not the pristine celestial sphere philosophers had imagined. Jupiter showed 4 small points of light that moved around it from night to night, moons orbiting another planet, proving that not everything in the cosmos orbited Earth. Venus went through phases like our moon, growing larger and smaller as it orbited the Sun, exactly as Copernicus's model predicted, but impossible to explain if Venus orbited Earth. Perhaps most astounding, when Galileo looked at the Milky Way, that cloudy band of light stretching across the sky, his telescope revealed it to be composed of countless individual stars, too numerous and too faint to distinguish with the naked eye. The universe, already known to be large, suddenly expanded beyond anything previously imagined. Those fuzzy patches weren't clouds or atmospheric phenomena but vast congregations of stars stretching into unimaginable distances. The telescope that Galileo first turned skyward in 1609 had a magnifying power of about 8 to 9 times, roughly equivalent to modern binoculars. Within a year, he had improved his designs to achieve magnifications of 20 to 30 times. This might seem modest by modern standards, but it was enough to reveal an entirely new cosmos. Each improvement in telescope technology would continue this pattern throughout history. Better optics meant deeper views into space, and deeper views meant revolutionary discoveries about the nature of the universe. And so the foundation was laid, from ancient observers noticing 5 wandering points of light among the fixed stars, through Ptolemy's complex geocentric system with its epicycles and deferents, to Copernicus's elegant heliocentric revolution placing the Sun at the center. We followed Kepler's discovery that orbits are ellipses, not circles, that planets sweep equal areas in equal times, and that orbital period and distance follow a mathematical law connecting the square of one to the cube of the other. We witnessed Galileo's telescope revealing the Moon's mountains and craters, Jupiter's 4 moons proving not everything orbits Earth, Venus's phases confirming heliocentric predictions, and the Milky Way dissolving into countless stars. Each discovery was a step away from Earth-centered thinking toward understanding our true place in a cosmos far larger and more intricate than our ancestors could have dreamed. Feel yourself floating now, weightless and peaceful, like drifting in the gentle darkness between stars. There's no up or down here, no effort required, just the calm suspension in infinite space. Let the story carry you deeper into rest, deeper into the welcoming darkness where sleep waits patiently. As our journey through space science continues, we arrive at one of the most profound intellectual achievements in human history, the moment when someone finally explained why Kepler's laws worked, why planets orbit as they do, and what invisible force holds the cosmos together. That someone was Isaac Newton, an English mathematician and physicist working in the late 17th century. In 1687, Newton published his masterwork, the Principia Mathematica, which laid out his 3 laws of motion and his law of universal gravitation. The story goes that Newton's insight came from watching an apple fall from a tree, probably apocryphal, but it captures an essential truth. Newton realized that the same force pulling the apple downward might extend far beyond Earth's surface, reaching all the way to the moon and beyond. Newton's law of universal gravitation stated that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. In simpler terms, massive objects pull harder, and objects farther apart pull more weakly, following a precise mathematical relationship. This single equation, elegant in its simplicity, explained everything from falling apples to planetary orbits to the tides in Earth's oceans, which Newton correctly attributed to the Moon's gravitational pull. What made Newton's achievement so remarkable was that it unified celestial and terrestrial physics. Before Newton, the heavens were thought to operate by different rules than earthly matter. Celestial motion was perfect and eternal, while earthly motion was imperfect and temporary. Newton showed this distinction was false. The same laws governing a cannonball's arc governed the Moon's orbit around Earth. The Moon, in Newton's framework, was essentially falling toward Earth continuously, but moving sideways fast enough that it kept missing the definition of an orbit. This insight transformed humanity's understanding of the cosmos from a collection of mysterious phenomena to a clockwork mechanism operating according to universal, discoverable laws. Newton's work also explained why Kepler's laws worked. The elliptical orbits, the equal-area law, the relationship between period and distance, all of these emerged naturally from the mathematics of gravitational attraction. Kepler had discovered the patterns through painstaking observation and calculation, but Newton revealed the underlying cause. It was gravity, acting across the vast emptiness of space, that choreographed the cosmic dance. The implications were staggering. If gravity operated according to mathematical laws, then with precise enough measurements and calculations, you could predict future planetary positions with perfect accuracy. Astronomers began creating detailed tables of planetary movements decades or even centuries into the future. Navigation improved as lunar and stellar positions could be predicted precisely. The universe became, in principle, predictable, a view that would dominate physics for the next 200 years. But Newton's laws also raised a troubling question. If gravity pulls everything together, why doesn't the universe collapse in on itself? Why do stars remain separated by vast distances instead of falling together into one enormous mass? Newton himself pondered this paradox, eventually suggesting that perhaps the universe was infinite, with stars distributed uniformly throughout infinite space. In such a universe, every star would be pulled equally in all directions by distant stars, creating a kind of gravitational balance. It was an ingenious solution, though not entirely satisfactory, and the question would continue to haunt cosmologists for centuries. As telescopes improved through the 18th and 19th centuries, astronomers discovered that the universe was far larger and more complex than even Galileo's revolutionary observations had suggested. William Herschel, a German-born British astronomer, constructed increasingly large telescopes in the late 1700s, including one with a mirror 48 inches across, an enormous instrument for its time, requiring elaborate scaffolding to operate. With these powerful telescopes, Herschel made a discovery that expanded the known solar system. In 1781, he found a new planet beyond Saturn. Named Uranus, it was the first planet discovered in recorded history. The 5 planets known to the ancients had been visible since prehistoric times, but Uranus was too dim to see without optical aid. Its distance from the Sun was approximately 19 astronomical units, an astronomical unit, or AU, being the distance from Earth to the Sun, about 150 million kilometers. Uranus took 84 Earth years to complete one orbit, a stately, slow journey around the distant Sun. But Uranus presented a puzzle. As astronomers tracked its orbit over subsequent decades, they noticed irregularities. The planet didn't move quite as Newton's laws predicted. Something was perturbing its orbit, pulling it slightly off course. 2 mathematicians, John Couch-Adams in England and Urbain Le Verrier in France, independently performed calculations suggesting that an even more distant planet might be responsible for these perturbations. They predicted where this unknown planet should be located based purely on its gravitational influence on Uranus. In 1846, German astronomer Johann Galle turned his telescope to the predicted position and found Neptune, almost exactly where the calculations said it should be. This discovery was a triumph of Newtonian physics, an entirely new world found not by searching the sky, but by analyzing gravitational anomalies mathematically. Neptune orbits at about 30 AU from the Sun, taking 165 Earth years to complete a single orbit. Since its discovery in 1846, Neptune has completed only slightly more than one full orbit as of now. These are timescales almost beyond human reckoning, yet governed by the same laws that make apples fall. The discovery of Neptune through mathematical prediction demonstrated the power of physics in its most pure form, understanding fundamental laws so well that you could deduce the existence of something you'd never seen. It also established a pattern that would repeat in physics, using discrepancies between theory and observation to discover new phenomena. When your measurements don't match your predictions, either your measurements are wrong, your theory is wrong, or something new is influencing the system. In this case, that something was an entire planet waiting to be discovered. As the 19th century progressed, astronomers turned their attention to understanding what stars actually were. They appeared as points of light, but were they distant suns like our own? How far away were they? What were they made of? The distances involved were so vast that traditional surveying methods used on Earth seemed hopeless. You couldn't exactly measure the distance to a star with a measuring tape or triangulation in any ordinary sense. But astronomers found a clever solution using Earth's orbit around the Sun. By observing a relatively nearby star from opposite sides of Earth's orbit, 6 months apart, astronomers could detect a tiny shift in the star's apparent position against the background of much more distant stars. This shift, called parallax, is the same effect you observe when you hold your finger at arm's length and look at it alternately with each eye. Your finger appears to shift position against the distant background. The amount of shift tells you the distance. The first successful stellar parallax measurement was made by Friedrich Bessel in 1838 for the star 61 Cygni. The parallax was incredibly small, less than 1/3 of an arcsecond, which is 1/3 of 1/60th of 1/60th of a degree, but measurable with the precision instruments available. This tiny angle revealed a staggering distance. 61 Cygni was approximately 11 light-years away, meaning light traveling at 300,000 kilometers per second took 11 years to reach Earth from that star. The star was roughly 660,000 times farther from Earth than the Sun, a distance so vast it defied intuitive comprehension. The measurement of stellar parallax gave humanity our first true sense of the cosmic distance scale. The solar system, already known to be enormous, was merely a tiny bubble in a universe of incomprehensible vastness. The nearest stars were separated from us by distances millions of times greater than the distances between planets. And these were the nearest stars. The Milky Way contained billions of them, stretching across distances that made even 11 light-years seem trivial. And so we've followed the story from Newton's universal gravitation in 1687, unifying celestial and terrestrial physics with a single elegant equation, explaining that the Moon continuously falls toward Earth while moving sideways fast enough to keep missing. The nature of orbit revealed. We learned that Newton's laws explained Kepler's observations, that gravity's mathematics made the universe predictable, yet raised the paradox of why the universe doesn't collapse on itself. We witnessed Herschel's discovery of Uranus in 1781, 19 astronomical units from the Sun, taking 84 years per orbit, the first planet found in recorded history. We followed the mathematical prediction of Neptune through gravitational perturbations, discovered in 1846 at 30 AU, taking 165 years to orbit, found almost exactly where calculations placed it, a pure triumph of Newtonian physics. We learned that Bessel measured the first stellar parallax in 1838, finding 61 Cygni 11 light-years away, 660,000 times Earth's distance from the Sun, a shift less than 1/3 of an arcsecond, revealing the true cosmic distance scale. Each discovery pushed our perspective outward, the universe expanding in our understanding with every measurement, every calculation, every patient observation through improved telescopes. Feel yourself drifting through those vast distances now, floating peacefully in the darkness between stars, time and space stretching out infinitely around you. But you're safe here, weightless and calm, carried gently by the story deeper into rest, deeper into the welcoming embrace of sleep. As we continue our gentle journey through space science, we arrive at one of the most revolutionary developments in astronomy, the discovery that light itself could reveal the composition, temperature, and motion of distant stars, transforming astronomy from merely measuring positions and distances to understanding what celestial objects actually are. In the early 19th century, scientists discovered that when light passes through a prism and spreads into a rainbow spectrum, that spectrum isn't always continuous. Sometimes it contains dark lines, specific wavelengths of light that are missing. A German optician named Joseph von Fraunhofer observed hundreds of these dark lines in sunlight in 1814, cataloging their precise positions with meticulous care. These became known as Fraunhofer lines, though their meaning remained mysterious for decades. The breakthrough in understanding came in the 1850s and 1860s when scientists realized that every chemical element, when heated until it glows, produces light at specific characteristic wavelengths, a unique fingerprint of bright lines. Conversely, when light passes through a cool gas of that element, it absorbs those same specific wavelengths, creating dark lines in what would otherwise be a continuous spectrum. The pattern of lines in a spectrum reveals which elements are present in the light source or in the gas the light passes through. This technique, called spectroscopy, revolutionized astronomy when applied to starlight. By analyzing the pattern of dark lines in a star's spectrum, astronomers could determine what elements that star contained, even though the star was trillions of kilometers away and could never be visited or sampled directly. The Sun's spectrum revealed hydrogen, helium, iron, calcium, sodium, and dozens of other elements. In fact, helium was discovered in the Sun's spectrum in 1868, during a solar eclipse by Pierre Janssen and Norman Lockyer, before it was ever found on Earth, giving the element its name from Helios, the Greek word for sun. But spectroscopy revealed more than just composition. Scientists noticed that the pattern of spectral lines from some stars appeared shifted slightly toward the red end of the spectrum, while lines from other stars shifted toward the blue end. The explanation came from the Doppler effect, a phenomenon first described by Austrian physicist Christian Doppler in 1842. The Doppler effect explains why a train whistle sounds higher pitched as it approaches and lower pitched as it recedes. Motion toward you compresses waves, increasing frequency, while motion away stretches waves, decreasing frequency. The same principle applies to light. If a star is moving toward Earth, its light waves are compressed slightly, shifting the spectral lines toward shorter wavelengths, toward the blue end of the spectrum, a phenomenon called blue shift. If a star is moving away from Earth, its light waves are stretched, shifting lines toward longer wavelengths, toward the red end, called redshift. By measuring how much the lines had shifted, astronomers could calculate how fast a star was moving toward or away from us. For the first time, astronomy could measure not just positions and distances, but velocities, the three-dimensional motion of stars through space. This ability to measure stellar velocities led to a profound discovery about the nature of the Milky Way. In the early 20th century, astronomers began systematically measuring the motions of stars in different parts of the sky. They found that stars weren't moving randomly, but showed coordinated patterns suggesting the entire Milky Way was rotating like an enormous disk. Our Sun, along with billions of other stars, orbits the center of this disk at a speed of approximately 220 kilometers per second, roughly 800,000 kilometers per hour, yet takes about 225 to 250 million years to complete one orbit because the distances involved are so vast. Think about that for a moment. Our Sun, with all its planets including Earth, is racing through space at nearly 1,000,000 kilometers per hour, carrying us along on a galactic journey. The last time Earth was at this point in its galactic orbit, dinosaurs had not yet appeared. The entire span of human civilization, all of recorded history, represents just a tiny fraction of one galactic year. We live on timescales and spatial scales our minds can barely grasp. The recognition that the Milky Way was rotating raised new questions. What lay at the center? How large was the Milky Way? And what about those fuzzy patches of light scattered across the sky, called nebulae? Were they clouds within our Milky Way, or were they something else entirely? The question of nebulae led to one of the great astronomical debates of the early 20th century. Some astronomers, like Harlow Shapley, believed nebulae were relatively small objects within our Milky Way galaxy. Others, like Heber Curtis, argued that some nebulae might be island universes, entire galaxies like our own, located at enormous distances beyond the Milky Way. The debate came to a head in 1920 in what became known as the Great Debate, with Shapley and Curtis presenting their cases to the scientific community. At the time, neither side had definitive proof. The resolution came in the 1920s through the work of Edwin Hubble, using what was then the world's largest telescope, the 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble focused on the Andromeda Nebula, one of the largest and brightest of these fuzzy patches. Within this nebula, he identified individual stars, including a type called Cepheid variables, stars that brighten and dim in a regular, predictable pattern. Crucially, astronomers had discovered that the period of a Cepheid's variation is directly related to its intrinsic brightness. This relationship, discovered by Henrietta Swan Leavitt in 1912 through painstaking analysis of thousands of photographic plates, meant that Cepheids could serve as standard candles. If you measured how long the variation period was, you knew how bright the star actually was. And by comparing that to how bright it appeared from Earth, you could calculate its distance. When Hubble measured the Cepheid variables in Andromeda, he found they were incredibly faint compared to their known intrinsic brightness. The calculations revealed that Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way, which was known to be roughly 100,000 light-years across. Andromeda wasn't a nebula within our galaxy, it was an entire galaxy unto itself, comparable in size to the Milky Way, containing hundreds of billions of stars. The universe had suddenly expanded again, just as it had when Galileo revealed the true nature of the Milky Way 3 centuries earlier. Hubble's discovery of the distance to Andromeda in 1924 transformed our cosmic perspective fundamentally. If Andromeda was a separate galaxy, then likely the other nebulae were galaxies too. The universe wasn't one great collection of stars called the Milky Way. It was a cosmos containing billions of separate galaxies, each containing billions of stars, separated by millions of light-years of mostly empty space. The scale was almost incomprehensible, yet measurable, knowable through patient observation and clever reasoning. And so we've learned how light became astronomy's most powerful tool. Fraunhofer cataloging hundreds of dark lines in sunlight in 1814, scientists in the 1850s-60s discovering that every element has a unique spectral fingerprint, helium discovered in the sun's spectrum in 1868 before ever being found on Earth. We discovered the Doppler effect revealing stellar motion through spectral shifts, blue shift from stars approaching, redshift from stars receding, allowing measurement of velocities through space for the first time. We learned that our Sun orbits the Milky Way center at 220 kilometers per second, taking 225 to 250 million years for one orbit, all of human civilization just a tiny fraction of one galactic year. We witnessed the great debate of 1920 between Shapley and Curtis about whether nebulae were within our galaxy or separate island universes. We followed Hubble's discovery in 1924 using Cepheid variables, stars whose variation period reveals intrinsic brightness, to measure Andromeda at 900,000 light-years away, proving it was a separate galaxy with hundreds of billions of stars, expanding the known universe from one galaxy to billions. Each revelation like opening curtains on ever larger stages, the cosmos growing in scope and majesty with every measurement. Feel yourself floating now through this vast space between galaxies, peaceful in the darkness, weightless and calm, carried by the gentle current of the story deeper into rest. As our journey through the cosmos continues, we arrive at perhaps the most startling discovery in the history of astronomy, one that fundamentally changed our understanding of the universe's nature and fate. This discovery came from Edwin Hubble's continued observations in the late 1920s, building on his groundbreaking work identifying distant galaxies. After establishing that galaxies existed beyond the Milky Way, Hubble began systematically measuring their distances and velocities. Using spectroscopy to measure redshift, he could determine how fast each galaxy was moving relative to Earth. What he discovered was completely unexpected. Nearly all galaxies showed redshift, meaning they were moving away from us. Even more remarkable, when he plotted distance against velocity, a clear pattern emerged. Galaxies that were farther away were receding faster, and the relationship was linear: double the distance, double the recession velocity. In 1929, Hubble published this relationship, now known as Hubble's law. The implications were staggering. The universe itself was expanding. It wasn't that galaxies were moving through static space away from some central point. Space itself was stretching, carrying galaxies along with it like raisins in rising bread dough. Every galaxy sees every other galaxy moving away, because the space between them is constantly growing. The Hubble constant, describing the rate of this expansion, was initially calculated to be about 500 kilometers per second per megaparsec, meaning for every megaparsec, about 3.26 million light-years of distance, recession velocity increased by 500 kilometers per second. Modern measurements have refined this value to approximately 70 kilometers per second per megaparsec, but the fundamental discovery remained: we live in an expanding universe. This discovery of cosmic expansion led to a profound realization: if the universe is expanding now, it must have been smaller in the past. Running the expansion backward in time, everything in the universe must have once been compressed together in an extremely hot, dense state. This idea, initially proposed by Belgian priest and physicist Georges Lemaitre in 1927 and later refined by George Gamow and others, became known as the Big Bang Theory. The universe, according to this model, began approximately 13.8 billion years ago from an incredibly hot, dense initial state and has been expanding and cooling ever since. The Big Bang Theory made specific predictions that could be tested. One prediction, developed by Gamow and his colleagues Ralph Offer and Robert Herman in 1948, was that the universe should be filled with a faint afterglow of radiation left over from the hot early universe, a cosmic microwave background radiation. As the universe expanded and cooled, the initially intense radiation would have been stretched to longer wavelengths, becoming microwave radiation with a temperature of just a few degrees above absolute zero. In 1964, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were testing a sensitive microwave antenna when they detected a persistent background noise that wouldn't go away no matter which direction they pointed the antenna or what time of day they observed. After eliminating all possible sources of interference, including famously cleaning pigeon droppings from the antenna, they concluded the signal was real and coming from space itself. What they had discovered was the cosmic microwave background radiation, with a temperature of approximately 2.7 degrees Kelvin, almost exactly as predicted. This discovery, honored with the Nobel Prize in 1978, provided powerful confirmation of the Big Bang Theory and gave us a snapshot of the universe when it was just 378,000 years old, the moment when it had cooled enough for atoms to form and light to travel freely through space. While astronomers were unraveling the universe's large-scale structure and history, other scientists were exploring the opposite extreme, the world of the incredibly small, and what it revealed about the nature of matter and energy. This journey into quantum mechanics would prove essential for understanding how stars work, why they shine, and what happens in the extreme conditions of the early universe. In the early 20th century, physicists discovered that energy comes in discrete packets called quanta, rather than being infinitely divisible. This quantum nature of reality was deeply counterintuitive. It meant that at the smallest scales, nature is fundamentally grainy rather than smooth. Max Planck introduced the quantum concept in 1900 to explain how hot objects emit radiation. Albert Einstein expanded it in 1905, showing that light itself comes in quantum packets called photons, particles of light, each carrying a specific amount of energy related to its wavelength. This dual nature of light, behaving both as a wave and as discrete particles, became one of the foundational insights of quantum mechanics. The quantum revolution transformed our understanding of atoms. In 1913, Danish physicist Niels Bohr developed the model of the atom where electrons orbit the nucleus only at specific, discrete energy levels. They can jump from one level to another by absorbing or emitting a photon of exactly the right energy, but they can't exist at energies in between. This explained why atoms absorb and emit light at specific wavelengths, creating those spectral lines that had proven so useful in astronomy. Each line represented an electron jumping between specific energy levels in an atom. But the most important application of quantum mechanics to space science came from understanding nuclear fusion, the process that powers stars. In the 1920s and 1930s, physicists including Arthur Eddington and Hans Bethe worked out that stars shine by fusing hydrogen nuclei together to form helium in their cores. At the enormous temperatures and pressures in a star's core, the Sun's core reaches about 15 million degrees Celsius. Hydrogen nuclei moving at tremendous speeds can overcome their electrical repulsion and fuse together through quantum mechanical tunneling. In the Sun's core, for hydrogen nuclei, protons eventually combine through a series of reactions to form one helium nucleus. The helium nucleus has slightly less mass than the 4 protons that went into making it. This missing mass is converted to energy according to Einstein's famous equation E=mc², where c is the speed of light, approximately 300,000 kilometers per second. Because c is such a large number, and it's squared in the equation, even a tiny amount of mass converts to enormous energy. Every second, the Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium, 4 million tons of matter transformed entirely into energy, radiating outward as light and heat. This understanding of stellar fusion explained why stars shine for billions of years without running out of fuel. The Sun has been shining steadily for about 4.6 billion years and has enough hydrogen fuel to continue for another 5 billion years or so. But it also revealed that stars have life cycles. They're born when clouds of gas and dust collapse under gravity. They spend most of their lives fusing hydrogen in their cores, and they eventually die when they exhaust their nuclear fuel. What happens in a star's death depends on its mass, leading to some of the universe's most extreme phenomena. And so we've discovered the expanding universe, Hubble's 1929 law showing galaxies receding faster with greater distance, initially calculated at 500 kilometers per second per megaparsec, refined to about 70 today. Space itself stretches like rising bread dough, carrying galaxies with it, every galaxy seeing every other receding. We learned that expansion implies a beginning, the Big Bang approximately 13.8 billion years ago from an incredibly hot, dense state. We followed the prediction of cosmic microwave background radiation by Gamow, Alpher, and Herman in 1948, discovered by Penzias and Wilson in 1964 at 2.7 Kelvin, showing the universe when it was just 378,000 years old. We descended into the quantum realm, Planck's quanta in 1900, Einstein's photons in 1905, Bohr's discrete atomic energy levels in 1913 explaining spectral lines as electron jumps. We learned fusion powers stars through quantum tunneling at 15 million degrees Celsius core temperature, converting 4 million tons of mass to pure energy every second via E=mc², the Sun shining steadily for 4.6 billion years with 5 billion more to go. Each discovery connecting the vast and the tiny, the ancient and the energetic, weaving together a cosmos that makes sense through patient observation and brilliant reasoning. Feel the energy of starlight washing over you now, ancient photons that began their journey millions of years ago, arriving gently, peacefully, carrying you deeper into rest. As we continue our gentle drift through the history of space science, we arrive at the dramatic discoveries about stellar death and the exotic objects that remain when stars exhaust their fuel. These revelations showed that the universe contains phenomena far stranger than anyone had imagined, objects so dense and extreme they challenged our understanding of physics itself. For stars with mass similar to our Sun, death is a relatively gentle process. When such a star exhausts the hydrogen in its core after billions of years of fusion, it begins fusing helium into carbon and oxygen. The outer layers expand dramatically, and the star becomes a red giant, enormous in size but cooler at the surface, giving it a reddish color. Eventually, the outer layers drift away into space, forming a beautiful expanding shell called a planetary nebula. The name is misleading, as these have nothing to do with planets, but early observers thought they resembled planetary disks through their telescopes. What remains at the center is the star's hot, dense core, a white dwarf. A white dwarf is an extraordinary object. It contains roughly the mass of the Sun compressed into a volume about the size of Earth. A cubic centimeter of white dwarf material would weigh approximately 1 ton. This incredible density is supported not by fusion or thermal pressure, but by quantum mechanical degeneracy pressure, a consequence of the Pauli exclusion principle, which states that no two electrons can occupy exactly the same quantum state. When matter is compressed enough, electrons are forced into higher and higher energy states, and their resistance to further compression supports the white dwarf against gravitational collapse. A white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark black dwarf, though the universe isn't old enough yet for any black dwarfs to exist. But for stars with more than about 8 to 10 times the Sun's mass, death is far more violent and spectacular. These massive stars fuse progressively heavier elements in their cores, hydrogen to helium, helium to carbon and oxygen, carbon to neon and magnesium, and so on, creating layers like an onion, with each shell fusing different elements. Finally, the core begins fusing silicon into iron. Here, the process stops. Iron is the most stable atomic nucleus. Fusing iron into heavier elements doesn't release energy, it consumes energy. When the core becomes primarily iron, fusion ceases, and without the outward pressure from fusion to balance gravity, catastrophe strikes. The iron core collapses in less than a second, compressing matter to nuclear densities, the mass of the Sun crushed into a sphere just 20 to 30 kilometers across. The collapse happens so rapidly that the outer layers of the star are still falling inward when the core rebounds, creating a shockwave that races outward through the star. The result is a supernova explosion, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars, releasing in that brief time more energy than the Sun will produce in its entire 10 billion-year lifetime. Supernovae were observed by ancient and medieval astronomers as guest stars that suddenly appeared in the sky where no star had been visible before, shone brilliantly for weeks or months, then faded away. The Chinese recorded a supernova in 1054 CE that was visible in daylight for 23 days. Modern telescopes have found the remnant of this explosion, the Crab Nebula, an expanding cloud of glowing gas and dust still rushing outward from the explosion site nearly 1,000 years later, expanding at speeds of approximately 1,500 kilometers per second. But perhaps the most important legacy of supernovae is what they create. During the explosion, the intense heat and pressure allow fusion to continue beyond iron, creating all the heavy elements in the periodic table: gold, silver, uranium, and everything else heavier than iron. These elements are blasted into space by the explosion, mixing with the interstellar gas and eventually incorporating into new generations of stars and planets. Every atom of gold in your jewelry, every atom of calcium in your bones, every atom of iron in your blood was forged in a supernova explosion billions of years ago. We are, quite literally, made of stardust, the remnants of stars that died before our solar system was born. What remains after a supernova depends on the original star's mass. For stars in a certain mass range, the collapsed core becomes a neutron star, an object so dense that protons and electrons are crushed together to form neutrons, creating matter at nuclear density. A neutron star typically contains 1.4 to 2 times the Sun's mass compressed into a sphere just 20 to 25 kilometers in diameter. A teaspoon of neutron star material would weigh about 1 billion tons on Earth, roughly the mass of Mount Everest compressed into something you could hold in your hand, if that were somehow possible. Neutron stars have other extraordinary properties. Many rotate extremely rapidly, some spinning hundreds of times per second, a consequence of conservation of angular momentum as the original star's core collapsed. Some neutron stars have incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field. When these magnetic fields channel particles along the magnetic poles, they create beams of radiation that sweep through space like a lighthouse beam. If Earth happens to lie in the path of this beam, we detect regular pulses of radio waves as the neutron star rotates, sometimes with astonishing precision, down to microseconds. These objects, discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, are called pulsars. The first pulsar discovered, designated PSRB 1919+21, pulsed with a period of 1.3 seconds, so regular that the discovery team briefly considered whether it might be an artificial signal from an alien civilization, jokingly calling it LGM-14 Little Green Men. But further observations found more pulsars with different periods, and the natural explanation became clear: these were rapidly rotating neutron stars. Some pulsars are so incredibly regular in their rotation that they rival atomic clocks in precision. The most stable pulsars, called millisecond pulsars, deviate from perfect regularity by less than 1 part in 10 to the power of 15, timing precision that allows them to be used as cosmic timekeepers for testing fundamental physics. But neutron stars aren't the most extreme outcome of stellar death. For the most massive stars, the core collapse doesn't stop at neutron degeneracy pressure. If the collapsing core exceeds approximately 3 times the Sun's mass, a limit called the Tolman-Oppenheimer-Fokoff limit, even neutron degeneracy pressure cannot halt the collapse. Gravity overwhelms all resistance, and the core continues collapsing past the neutron star stage into an object so dense and with such powerful gravity that even light cannot escape, a black hole. The concept of black holes emerged from Einstein's general theory of relativity, published in 1915. Einstein's theory described gravity not as a force, as Newton had conceived it, but as the curvature of spacetime caused by mass and energy. Massive objects bend the fabric of spacetime, and other objects move along the curves in this fabric. What we perceive as gravitational attraction is actually objects following the straightest possible paths through curved spacetime. Just months after Einstein published his theory, German physicist Karl Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a spherical mass. Schwarzschild's solution revealed something remarkable. If enough mass was compressed within a small enough radius, later called the Schwarzschild radius, the spacetime curvature would become so extreme that a boundary would form from which nothing, not even light, could escape. For a mass equal to the Sun, the Schwarzschild radius is approximately 3 kilometers. If you could compress the sun's entire mass into a sphere just 3 kilometers in radius, far smaller than the approximately 20-kilometer radius of a neutron star, it would become a black hole. At the Schwarzschild radius, called the event horizon, escape velocity equals the speed of light. Anything that crosses the event horizon, whether matter or light, is trapped forever, unable to escape the black hole's gravitational grip. And so we've witnessed stellar death in its forms, sun-like stars becoming red giants, shedding outer layers as planetary nebulae, leaving white dwarfs with 1 ton per cubic centimeter, supported by electron degeneracy pressure, cooling slowly over trillions of years in a universe not yet old enough for black dwarfs to exist. We followed massive stars through their fusion stages, hydrogen to helium to carbon to oxygen to iron, then catastrophic core collapse in less than 1 second when fusion stops at iron, rebounding into supernova explosions outshining entire galaxies. The 1054 CE supernova visible in daylight for 23 days, now the Crab Nebula expanding at 1500 kilometers per second. We learned that supernovae forge all elements heavier than iron, blasting them into space. We are made of stardust from explosions before our solar system formed. We discovered neutron stars at nuclear density, 1.4 to 2 solar masses in 20 to 25 kilometer spheres, a teaspoon weighing 1 billion tons. We found pulsars discovered in 1967, neutron stars spinning hundreds of times per second with trillion-fold stronger magnetic fields than Earth, some stable to 1 part in 10 to the power of 15. And we approached the ultimate extreme, black holes from Einstein's 1915 relativity, Schwarzschild solution showing masses compressed within their Schwarzschild radius create event horizons from which even light cannot escape, 3 kilometers for a solar mass. Feel yourself approaching that event horizon now, not with fear but with peaceful surrender, crossing into the total darkness of sleep, where time loses meaning and consciousness fades, drawn irresistibly into the perfect rest that waits beyond. As we continue our peaceful journey through the cosmos, we arrive at one of the most transformative eras in space science, the space age, when humanity finally broke free from Earth's surface and began directly exploring the solar system and beyond. This journey from theory to practice, from telescopes to spacecraft, opened entirely new ways of understanding our cosmic neighborhood. The space age began on October 4, 1957, when the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. Sputnik was a simple sphere just 58 centimeters in diameter, weighing about 83 kilograms, with 4 external radio antennas that broadcast a simple beeping signal as it circled the Earth every 96 minutes. That beeping sound, received by radio operators around the world, announced that humanity had entered a new era. For the first time, a human-made object was orbiting our planet, traveling through the vacuum of space at approximately 29,000 kilometers per hour, about 8 kilometers per second. Sputnik's success shocked the world, particularly the United States, and ignited what became known as the space race, a competition between the Soviet Union and the United States to achieve milestones in space exploration. Just 1 month after Sputnik, the Soviets launched Sputnik 2, carrying the first living creature into orbit, a dog named Laika. Tragically, the technology to safely return Laika to Earth didn't yet exist, and she died within hours from overheating and stress. But her journey demonstrated that living organisms could survive launch and the weightlessness of orbital flight, paving the way for human spaceflight. The next great milestone came on April 12, 1961, when Soviet cosmonaut Yuri Gagarin became the first human in space, orbiting Earth once aboard the Vostok 1 spacecraft. Gagarin's flight lasted just 108 minutes from launch to landing, but it was a profound moment in human history. A member of our species had left the planet, seen Earth from space as a blue sphere against the blackness, and returned safely. Gagarin described Earth as beautiful, saying the Earth is blue. How wonderful! It is amazing. This perspective, seeing our planet as a finite, fragile world suspended in space, would later be called the overview effect, a shift in consciousness reported by many astronauts upon viewing Earth from orbit. The United States responded to these Soviet achievements by committing to an even more ambitious goal. On May 25, 1961, just weeks after Gagarin's flight, President John F. Kennedy addressed Congress and announced, "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth." It was an audacious declaration. At that moment, the United States had achieved only 15 minutes of human spaceflight with Alan Shepard's suborbital flight weeks earlier. Reaching the moon would require technology that didn't yet exist, rockets far more powerful than any built, and solutions to problems that hadn't even been fully identified. Yet just 8 years later, the goal was achieved. On July 20, 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin landed the lunar module Eagle in the Moon's Sea of Tranquility while Michael Collins orbited above in the command module Columbia. At 10:56 p.m. Eastern Daylight Time, Armstrong descended the ladder, planted his foot on the lunar surface, and spoke the famous words, "That's one small step for man, one giant leap for mankind." For the first time, humans stood on another world, not Earth, but a celestial body that had orbited our planet for billions of years, now hosting visitors from the world it circles. The Apollo program eventually landed 12 astronauts on the moon across 6 missions between 1969 and 1972, with Apollo 13 famously failing to land but successfully returning its crew safely after an oxygen tank explosion. The astronauts brought back 382 kilograms of lunar rock and soil samples, precious cargo that has been studied intensively ever since. These samples revealed that the moon is made of material similar to Earth's mantle, supporting the giant impact hypothesis, the theory that the moon formed about 4.5 billion years ago when a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, which gradually coalesced into the moon. This violent birth explained many of the moon's properties, why it's so large relative to Earth compared to other planet-moon systems, why it has a relatively small iron core, and why lunar rocks have similar isotopic compositions to Earth rocks. While humans were reaching the moon, robotic spacecraft were beginning to explore the other planets of our solar system, going where humans couldn't yet venture. These missions transformed planets from points of light and telescopes into real worlds with their own landscapes, weather, and mysteries. The first successful interplanetary mission was Mariner 2, which flew past Venus in 1962, discovering that Venus's surface temperature was approximately 460 degrees Celsius, far hotter than Mercury despite being farther from the Sun. This intense heat, caused by a runaway greenhouse effect from Venus's thick carbon dioxide atmosphere, made Venus the hottest planet in the solar system and dashed early hopes that it might harbor life beneath its cloud cover. Mars became a major target of exploration, with NASA's Mariner 4 becoming the first spacecraft to successfully fly by Mars in 1965, sending back 22 grainy images that revealed a cratered, apparently dead world, quite different from the Mars of science fiction. Later missions painted a more complex picture. The Viking landers, which reached Mars in 1976, were the first spacecraft to successfully land on Mars and send back images from the surface. They revealed a rust-colored desert landscape beneath a pink sky, the color caused by fine dust suspended in the thin atmosphere. The Viking landers also carried experiments designed to detect signs of life, though the results were ambiguous and continue to be debated. The outer solar system proved even more spectacular. Pioneer 10 and 11, launched in the early 1970s, became the first spacecraft to travel through the asteroid belt and reach Jupiter. When Pioneer 11 continued on to Saturn, it sent back the first close-up images of the ringed planet. But it was the Voyager missions, launched in 1977, that truly transformed our understanding of the outer planets. Voyager 1 and 2 took advantage of a rare planetary alignment that occurs only once every 176 years, allowing them to visit Jupiter, Saturn, Uranus, and Neptune using gravity assists, using each planet's gravity to slingshot the spacecraft onward to the next destination with minimal fuel expenditure. The Voyager missions revealed the outer solar system as a realm of wonders. Jupiter's Great Red Spot turned out to be a storm larger than Earth that has raged for at least 350 years, possibly much longer. Jupiter's moon Io was discovered to be the most volcanically active body in the solar system, with plumes of sulfur erupting hundreds of kilometers above its surface, driven by tidal heating from Jupiter's powerful gravity. Europa showed a smooth, icy surface crisscrossed with cracks, suggesting a subsurface ocean of liquid water beneath the ice, making it one of the most promising places to search for life beyond Earth. And so we left Earth, Sputnik 1 on October 4, 1957, a 58-centimeter sphere weighing 83 kilograms, circling Earth every 96 minutes at 8 kilometers per second, its beeping announcing humanity's entry to space. Laika followed and Sputnik 2 1 month later, first living creature in orbit, sadly dying within hours but proving organisms could survive launch in weightlessness. We witnessed Gagarin's 108-minute flight on April 12, 1961, seeing Earth as blue and wonderful, experiencing the overview effect. We followed Kennedy's May 25, 1961 commitment to reach the moon before decade's end, just weeks after America's 15-minute suborbital flight, achieved July 20, 1969 when Armstrong and Aldrin landed while Collins orbited above. We learned Apollo missions brought back 382 kilograms of lunar samples supporting the giant impact hypothesis, Theia colliding with young Earth 4.5 billion years ago, ejecting material that became the moon. We explored with robots where humans couldn't go, Mariner 2 finding Venus at 460 degrees Celsius in 1962, Viking landers revealing Mars's rust-colored landscape in 1976. We journeyed to the outer solar system with Voyagers launched 1977, using once every 176-year planetary alignment, discovering Jupiter's 350-year-old storm larger than Earth, Io's most volcanically active body with sulfur plumes hundreds of kilometers high, Europa's icy surface suggesting subsurface ocean beneath, all made of wonders we'd only imagined. Feel yourself traveling now on these peaceful trajectories, gravity-assisted through the darkness, no engine needed, just the gentle arc of orbital mechanics carrying you deeper into rest, deeper into the quiet cosmos of sleep. As we drift deeper into the story of space exploration, we arrive at one of the most remarkable achievements of the space age, the creation of a permanent human presence in space through orbital stations, and the development of reusable spacecraft that made space more accessible than ever before. The concept of a space station, a crewed outpost orbiting Earth where astronauts could live and work for extended periods, became reality in 1971 when the Soviet Union launched Salyut-1, the world's first space station. Salyut-1 was relatively small, about 15 meters long, and operated for only about 6 months, but it established the principle that humans could live in space for weeks at a time. The Soviets followed with more Salyut stations and eventually Mir, launched in 1986, which became the first modular space station, assembled in orbit piece by piece over several years. Mir hosted astronauts continuously from 1989 to 1999, with some cosmonauts living aboard for over a year at a time. Valery Polyakov holds the record for the longest single spaceflight, spending 437 consecutive days aboard Mir from January 1994 to March 1995, more than 14 months in the weightlessness of orbit. These long-duration missions revealed crucial information about how the human body responds to extended weightlessness. Without gravity's constant pull, bones lose density at a rate of about 1 to 2% per month, muscles atrophy despite exercise, and fluids shift toward the head, causing the puffy-faced appearance many astronauts develop in orbit. The heart, no longer needing to pump blood against gravity, becomes slightly smaller and weaker. These changes showed that while humans can adapt to living in space, we evolved for life under gravity, and extended spaceflight requires careful attention to exercise, nutrition, and medical monitoring to minimize the physiological toll. The United States took a different approach to space access with the development of the Space Shuttle, the world's first reusable orbital spacecraft. Unlike all previous spacecraft that could be used only once and either burned up on re-entry or splashed down in the ocean, the Space Shuttle was designed to launch like a rocket, operate in orbit like a spacecraft, and return to Earth by gliding to a runway landing like an airplane. The first orbital test flight occurred on April 12, 1981, exactly 20 years after Gagarin's historic flight, when Space Shuttle Columbia lifted off with astronauts John Young and Robert Crippen aboard. The shuttle program flew 135 missions over 30 years, from 1981 to 2011, deploying satellites, servicing the Hubble Space Telescope, conducting scientific experiments in its Spacelab module, and playing a crucial role in constructing the International Space Station. The shuttle could carry crews of up to 8 astronauts and payloads weighing up to 24,000 kilograms to orbit, far more than any previous spacecraft. Its cargo bay was large enough to hold a school bus, making it possible to deploy large satellites and telescope arrays that couldn't have reached orbit any other way. But the shuttle program also experienced tragedy. On January 28, 1986, Space Shuttle Challenger broke apart 73 seconds after launch when a rubber O-ring seal in one of its solid rocket boosters failed in the cold weather, allowing hot gases to escape and breach the external fuel tank. All 7 crew members were killed, including teacher Krista McAuliffe, who would have been the first teacher in space. Then on February 1, 2003, Space Shuttle Columbia disintegrated during re-entry when damage to its thermal protection system, caused by a piece of foam insulation breaking off the external tank during launch 16 days earlier, allowed superheated gases to penetrate the wing structure. Again, all 7 crew members perished. These disasters sobered the spaceflight community and led to important safety improvements, but they also highlighted the inherent risks of space travel and the bravery of those who venture beyond Earth's atmosphere. While the shuttle was flying, international cooperation in space was expanding. The International Space Station, or ISS, began assembly in orbit in 1998, representing a partnership among the United States, Russia, Europe, Japan, and Canada. The station is the largest human-made structure in orbit, stretching about 109 meters from end to end, roughly the length of an American football field, and weighing approximately 420 tons. It orbits Earth at an altitude of about 400 kilometers, circling the planet every 90 minutes at a speed of approximately 28,000 kilometers per hour, or about 7.7 kilometers per second. The ISS has been continuously inhabited since November 2, 2000, more than 24 years of permanent human presence in space, with rotating crews typically staying for 6-month increments. Astronauts aboard the ISS conduct scientific experiments that take advantage of the unique microgravity environment, studying everything from protein crystal growth for drug development to the behavior of fluids without gravity's influence to the long-term effects of space on the human body. The station also serves as a test bed for technologies needed for future deep space exploration, life support systems, power generation, radiation protection, and the psychological aspects of long-duration missions in isolated, confined environments. One of the ISS's most important contributions has been demonstrating international cooperation in space. Russian cosmonauts and American astronauts live and work side by side, despite political tensions between their home countries. The station's modules were built by different countries and launched on different rockets, some Russian, some American, some European, yet all fit together seamlessly in orbit. This cooperation suggests that space exploration might become a unifying force for humanity rather than another arena for conflict. Meanwhile, our robotic explorers continued pushing deeper into the solar system and beyond. The Voyager spacecraft, having completed their encounters with the outer planets, continued traveling outward, carrying golden records, gold-plated copper phonograph discs containing sounds and images representing life and culture on Earth, intended as messages to any intelligent beings who might encounter the spacecraft in the distant future. In August 2012, Voyager 1 became the first human-made object to enter interstellar space, the region between stars, beyond the influence of the Sun's solar wind. As of now, Voyager 1 is approximately 24 billion kilometers from Earth, so distant that radio signals traveling at the speed of light take over 22 hours to reach it. The study of planets beyond our solar system, exoplanets, emerged as one of the most exciting fields in space science. For decades, astronomers theorized that other stars might have planets, but detecting them proved extraordinarily difficult. Planets don't produce their own light, they only reflect their star's light, and they're incredibly tiny compared to their stars. Imagine trying to spot a firefly next to a searchlight from thousands of kilometers away. and you begin to understand the challenge. The breakthrough came in 1995 when Swiss astronomers Michel Mayor and Didier Queloz discovered the first confirmed exoplanet orbiting a Sun-like star, 51 Pegasi b, a gas giant planet about half Jupiter's mass orbiting its star every 4.2 days. They detected it using the radial velocity method, which looks for tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. The star and planet actually orbit their common center of mass, causing the star to shift slightly toward and away from Earth as the planet orbits. This shift creates tiny Doppler shifts in the star's spectrum, just detectable with sensitive instruments. The discovery, honored with the Nobel Prize in Physics in 2019, opened the floodgates. Astronomers have now confirmed over 5,000 exoplanets orbiting other stars. And so we've witnessed humanity's permanent presence in space. Salyut 1 in 1971, first space station, followed by Modular Mir in 1986. Hosting cosmonauts continuously 1989 to 1999, Polyakov's record 437 consecutive days from January 1994 to March 1995. We learned weightlessness causes bone density loss of 1 to 2% per month, muscle atrophy, fluid shifts upward, heart becoming smaller without gravity to work against. We followed the space shuttle from Columbia's first flight April 12, 1981, 20 years after Gagarin, through 135 missions over 30 years, carrying up to 8 astronauts and 24,000 kilograms, deploying satellites and building ISS, but losing Challenger in 1986 and Columbia in 2003, each tragedy claiming 7 crew members. We learned ISS assembly began 1998, 109 meters long, 420 tons, orbiting 400 kilometers up at 28,000 kilometers per hour, circling Earth every 90 minutes, continuously inhabited since November 2, 2000, over 24 years of permanent presence, demonstrating international cooperation through shared modules and rotating crews. We watched Voyager 1 enter interstellar space August 2012, now over 24 billion kilometers away with 22-plus-hour light travel time, carrying golden records for any future finders. And we celebrated the first exoplanet around a Sun-like star, 51 Pegasi b, discovered 1995 by Mayor and Queloz using radial velocity, Jupiter mass planet orbiting every 4.2 days, opening the floodgates to over 5,000 confirmed exoplanets. Feel yourself orbiting now in that peaceful weightlessness, floating free from Earth's pull, watching the planet turn below, the sun rising every 90 minutes, the stars wheeling overhead in the perfect silence of space, drifting deeper into rest with each gentle orbit. As we approach the completion of our journey through space science, we arrive at some of the most profound recent discoveries and the questions that continue to drive our exploration of the cosmos. These findings have reshaped our understanding of the universe's composition, structure, and ultimate fate. One of the most startling discoveries of the late 20th century came from studying distant supernovae. In the 1990s, 2 independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were using Type Ia supernovae as standard candles to measure cosmic distances and determine how much the universe's expansion was slowing down due to gravity. Type Ia supernovae occur when a white dwarf accumulates enough mass from a companion star to trigger runaway nuclear fusion, producing explosions of remarkably consistent brightness. This consistency makes them perfect cosmic distance markers. Measure how bright they appear, and you know how far away they are. But when these teams analyzed their data in 1998, they found something completely unexpected. Instead of slowing down, the universe's expansion was accelerating. Galaxies were moving apart faster now than they were in the past. This discovery, honored with the Nobel Prize in Physics in 2011, implied that some unknown force was pushing the universe apart, working against gravity's attractive pull. Scientists call this mysterious influence dark energy, though the name is more a label for our ignorance than an explanation. Dark energy appears to make up approximately 68% of the total energy content of the universe, yet we have no idea what it actually is. It's perhaps the deepest mystery in modern physics. The discovery of dark energy connected to earlier evidence for another invisible component of the universe, dark matter. Beginning in the 1970s, astronomer Vera Rubin and others measured the rotation speeds of galaxies and found something puzzling. Stars in the outer regions of galaxies were orbiting much faster than they should based on the visible matter. According to Newton's laws and our understanding of gravity, stars farther from a galaxy center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But galaxy rotation curves remain flat. Stars far from the center moved just as fast as those closer in. The only explanation that fit the observations was that galaxies contain far more mass than we can see, mass that doesn't emit, absorb, or reflect light, but whose gravity influences the motion of visible matter. This invisible mass became known as dark matter. Further evidence came from gravitational lensing, the bending of light by massive objects predicted by Einstein's general relativity. When astronomers mapped how light from distant galaxies was bent by the gravity of galaxy clusters in the foreground, the amount of bending indicated far more mass than the visible stars and gas could account for. Current estimates suggest that dark matter makes up approximately 27% of the universe's total mass energy content. Combined with dark energy at 68%, this means that ordinary matter, atoms, the stuff that makes up everything we can see, touch, and directly detect, constitutes only about 5% of the universe. We are, quite literally, a tiny minority in a cosmos dominated by things we cannot yet understand. While dark matter and dark energy revealed our ignorance about the universe's large-scale composition, other discoveries were revealing the incredible diversity of worlds beyond our solar system. The Kepler Space Telescope, launched in 2009, was designed specifically to search for exoplanets using the transit method, detecting the tiny dimming of a star's light when a planet passes in front of it from our perspective. Over its mission, Kepler monitored over 500,000 stars continuously, discovering over 2,700 confirmed exoplanets and thousands more candidates awaiting confirmation. Kepler's discoveries revealed that planetary systems are remarkably diverse. Some exoplanets orbit incredibly close to their stars, completing an orbit in just hours or days, with surface temperatures high enough to vaporize rock. Others are frozen worlds far from their suns, or massive gas giants many times Jupiter's size. Some orbit binary star systems, worlds with two suns in their sky, like the fictional planet Tatooine from Star Wars but real. Perhaps most exciting, Kepler found many Earth-sized planets orbiting in their star's habitable zone, the region where temperatures could allow liquid water to exist on the surface, and where life as we know it might potentially arise. One particularly intriguing discovery from Kepler and other searches is that small, rocky planets appear to be incredibly common. Statistical analysis of Kepler's data suggests that nearly every Sun-like star has at least one planet, and many have multiple planets. Estimates indicate there may be tens of billions of Earth-sized planets in the Milky Way galaxy alone, with billions of those in habitable zones. This doesn't mean these planets have life, we simply don't know yet, but it means the potential sites where life could exist are far more numerous than we imagined even a few decades ago. The search for life beyond Earth has also been transformed by discoveries closer to home, within our own solar system. We've already mentioned Europa, Jupiter's moon with a subsurface ocean, but it's not alone. Saturn's moon Enceladus also shows strong evidence of a liquid water ocean beneath its icy shell. In 2005, the Cassini spacecraft observed geysers of water vapor and ice particles erupting from cracks near Enceladus's south pole, shooting hundreds of kilometers into space. Analysis of the particles revealed not just water, but also organic molecules, carbon-based compounds that are the building blocks of life. The discovery that Enceladus has liquid water, organic molecules, and a heat source, from tidal heating, similar to Io, means it has three of the key ingredients thought necessary for life. Even Mars, long considered a cold, dry, dead world, has revealed evidence of a watery past. Multiple Mars rovers and orbiters have found ancient riverbeds, deltas, and mineral deposits that only form in the presence of liquid water. The Mars rover Curiosity, which landed in 2012 in Gale Crater, found evidence that the crater once held a lake billions of years ago, with conditions that could have been suitable for microbial life. While we haven't found life on Mars, past or present, the possibility that the planet was once habitable has made it a prime target for astrobiological research. The Perseverance rover, which landed in 2021 in Jezero Crater, another ancient lake bed, is specifically designed to search for signs of ancient microbial life and is collecting samples that might eventually be returned to Earth for detailed analysis. The technological advances that have driven these discoveries continue to accelerate. The James Webb Space Telescope, launched on December 25, 2021, is the largest and most powerful space telescope ever built, with a primary mirror 6.5 meters in diameter, about 2.5 times larger than Hubble's. Webb observes primarily in infrared wavelengths, allowing it to peer through cosmic dust clouds that obscure visible light and to see the most distant galaxies in the universe, whose light has been redshifted into the infrared by cosmic expansion. Webb's early observations have been breathtaking. It has captured images of galaxies formed just a few 100 million years after the Big Bang, some of the first galaxies to light up the universe. It has analyzed the atmospheres of exoplanets by observing starlight filtering through those atmospheres during transits, detecting the chemical signatures of water vapor, carbon dioxide, methane, and other molecules. It has revealed star-forming regions in unprecedented detail, showing where new stars and planetary systems are being born in clouds of gas and dust. Each image and spectrum from Webb pushes the boundaries of our knowledge, answering old questions while raising new ones. And so we've discovered our cosmic ignorance made tangible. 1998 observations of Type Ia supernovae revealing accelerating expansion instead of slowing, implying dark energy making up approximately 68% of the universe. The Deepest Mystery in Physics, Nobel Prize 2011. We learned of Vera Rubin's 1970s galaxy rotation curve showing stars orbiting too fast for visible matter, implying dark matter at approximately 27% of cosmic mass energy, confirmed by gravitational lensing showing mass bending light beyond what visible matter could explain. Ordinary atoms, everything we can see and touch, constitute only about 5% of the universe. We followed Kepler's Space Telescope launched 2009, monitoring over 500,000 stars, discovering over 2,700 confirmed exoplanets showing remarkable diversity, worlds orbiting in hours, frozen distant giants, planets in binary star systems, many Earth-sized worlds and habitable zones. Statistical analysis suggests nearly every Sun-like star has planets, billions of Earth-sized worlds in our galaxy alone. We found subsurface oceans beyond Earth, Europa and Enceladus with liquid water beneath ice, Cassini observing Enceladus's geysers in 2005 containing water vapor, ice particles, and organic molecules. Mars rovers found ancient riverbeds and lake deposits, Curiosity landing in Gale Crater in 2012 finding evidence of ancient habitable conditions, Perseverance in Jezero Crater since 2021 searching for ancient microbial life signs. We witnessed James Webb Space Telescope launched December 25, 2021, 6.5-meter mirror observing in infrared, capturing galaxies from few hundred million years after Big Bang, analyzing exoplanet atmospheres detecting water, carbon dioxide, methane, revealing star-forming regions in unprecedented detail. Feel yourself expanding now with the universe, gently accelerating into the peaceful darkness, surrounded by mysteries that invite wonder rather than anxiety, floating through the cosmic ocean where questions outnumber answers, and that's perfectly fine, drifting deeper into the restful unknown. As we drift toward the end of our cosmic journey, let's gather the final threads of discovery, the questions that still call to us from the darkness, the mysteries that remind us how much wonder remains. In recent years, scientists have begun to understand something remarkable about the universe's timeline, its story written in light and mathematics, readable if you know how to look. The cosmic microwave background radiation we discovered earlier, that faint afterglow from when the universe was just 378,000 years old, has been mapped in exquisite detail by satellites like WMAP and Planck, revealing tiny temperature variations. Just a few millionths of a degree, across different patches of the sky. These tiny fluctuations, these whispers from the infant universe, tell us something profound. They represent density variations in the early cosmos, regions slightly denser than average, and regions slightly less dense. Over billions of years, gravity amplified these tiny differences, denser regions attracting more matter, growing into the galaxies and galaxy clusters we see today. The pattern of these fluctuations matches theoretical predictions with stunning precision, confirming our understanding of cosmic evolution, and allowing us to measure the universe's age, its composition, its geometry, with remarkable accuracy. From these observations, we now know the universe is 13.8 billion years old, give or take about 20 million years. We know it's flat in its overall geometry, meaning parallel lines stay parallel across cosmic distances, and we know the precise recipe of its contents: 5% ordinary matter, 27% dark matter, 68% dark energy, numbers that would have seemed like science fiction, yet emerged from patient observation and careful analysis. But knowing these numbers raises deeper questions, questions we're only beginning to ask, let alone answer. Consider the question of cosmic inflation, a theory proposed by physicist Alan Guth in 1980. Suggesting that in the first tiny fraction of a second after the Big Bang, the universe underwent exponential expansion, growing from smaller than an atom to macroscopic size, in less than a trillionth of a trillionth of a trillionth of a second. This sounds absurd, impossible, yet inflation elegantly explains several puzzling observations: why the universe looks approximately the same in all directions, why it's so precisely flat, and where those tiny density fluctuations came from. Quantum fluctuations stretch to cosmic scales during inflation. Evidence supporting inflation comes from precise measurements of the cosmic microwave background, its uniformity, its fluctuation pattern, all matching inflation's predictions. Yet inflation itself remains mysterious, driven by a hypothetical field called the inflaton, about which we know almost nothing. Some versions of inflation theory suggest our universe might be just one bubble in an eternally inflating multiverse, where new universes constantly spawn, each potentially with different physical laws, different constants of nature, most unable to support structures, stars, life, consciousness, and we find ourselves in one of the rare bubbles, where the laws happen to allow complexity, not because we're special, but because only in such universes could observers arise to ask the question. This is the anthropic principle, the idea that we observe the universe having properties compatible with our existence, because we couldn't exist to observe any other kind. It's philosophically unsettling, scientifically controversial, yet perhaps pointing toward truth, in ways we're still learning to understand. Meanwhile, closer to home, humanity stands at the threshold of returning to deep space, not just in orbit, but venturing back to the moon, and forward to Mars. NASA's Artemis program aims to land astronauts on the moon again, the first since 1972. Establishing permanent lunar bases, learning to live and work on another world, extracting resources, water ice in permanently shadowed craters, potentially providing drinking water, breathable oxygen, even rocket fuel, making the moon a stepping stone, rather than a destination. Mars beckons too. SpaceX and other organizations developing capabilities for crewed Mars missions. Perhaps in the 2030s or 2040s, the journey would take 6 to 9 months each way, astronauts spending over a year on the surface, waiting for orbital mechanics to align for the return trip. It's ambitious, dangerous, expensive, yet possibly inevitable, the next chapter in humanity's story of exploration. And perhaps, someday, we'll answer the question that underlies so much of our cosmic curiosity: are we alone, or does life exist elsewhere, in this vast universe? The search for extraterrestrial intelligence. SETI has listened for artificial radio signals from other civilizations since 1960. Frank Drake's Project Ozma, pointing a radio telescope at nearby sun-like stars, listening for patterns that couldn't arise naturally. In 1961, Drake formulated his famous equation, estimating the number of detectable civilizations in our galaxy by multiplying factors: the rate of star formation, the fraction with planets, the number of habitable planets per system, the fraction where life arises, where intelligence develops, where technology emerges, and how long technological civilizations last. The equation's power isn't in giving a definite answer. Most of the factors remain uncertain, but in organizing our ignorance, showing what we need to learn. Some factors we now know: nearly every star has planets. Habitable zone planets are common, others remain mysterious. How often does life begin? How likely is intelligence? How long do civilizations survive? These questions echo through the silence of our searches. So far, that silence continues. Decades of listening, improved technology, more sensitivity, yet no confirmed signals from other civilizations. This absence itself is puzzling, called the Fermi paradox after physicist Enrico Fermi, who asked, if intelligent life is common, where is everybody? Why don't we see evidence of galactic civilizations, megastructures, colonization waves, something? Many possible explanations exist. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations destroy themselves. Perhaps they lose interest in expansion. Perhaps interstellar travel remains impossible. Or perhaps they're here but hidden, or communicating in ways we haven't imagined. Or perhaps we're simply early, among the first to look up and wonder, in a universe just now waking to self-awareness. And so, dear traveler, we've journeyed far together tonight, from ancient observers noting 5 wandering lights, to Copernicus placing the sun at the center, Kepler finding ellipses, Newton revealing gravity's universal law, Bessel measuring the first stellar distance, 11 light-years, and realizing the cosmos was far larger than imagined. We followed Hubble discovering galaxies beyond our own, then the expanding universe, leading back to the Big Bang, 13.8 billion years ago, confirmed by the cosmic microwave background, that faint whisper of creation still echoing through space. We learned of quantum mechanics explaining how stars shine, fusion in the core, mass becoming energy, and how stars die, white dwarfs for the small, supernovae and neutron stars for the large, black holes for the most massive, where spacetime curves so severely, even light cannot escape. We witnessed humanity leaving Earth. Sputnik's beeps in 1957. Gagarin's orbit in 1961. Armstrong's footstep in 1969. Robotic explorers visiting every planet. Voyager entering interstellar space. The ISS hosting continuous human presence for over 2 decades. Kepler discovering thousands of worlds. Webb peering back to the universe's infancy. We discovered our universe is strange beyond imagination, 95% composed of dark matter and dark energy we don't understand, yet precisely measurable, predictable, knowable in ways our ancestors couldn't have dreamed. And we learn that wonder grows. The more we discover, the more questions emerge, each answer revealing deeper mysteries. Inflation and multiverses, the anthropic principle, the search for life beyond Earth, the great silence that might mean we're rare, or early, or simply not listening in the right way yet. 100 facts, woven into story, the story of how we learned where we are, and what we are, creatures of stardust on a small world, orbiting an ordinary star, in one galaxy among billions, looking outward with wonder, asking questions, seeking understanding, building knowledge fact by fact, generation after generation. But tonight, all that seeking can rest, all those questions can wait. The universe will still be here tomorrow, still expanding, still mysterious, still beautiful, still calling to us. For now, you need only rest, floating in the gentle darkness, weightless and peaceful, no gravity holding you, no questions requiring answers, just the infinite peaceful darkness of space, and sleep, and dreams. Your breathing is slow, like the patient rotation of galaxies. Your heartbeat is steady, like pulsars marking cosmic time. Your thoughts are drifting apart, like galaxies in the expanding universe, each one growing more distant, more faint, until there's only peaceful darkness, and silence, and rest. The journey is complete. You've traveled 13.8 billion years of cosmic history, from the Big Bang to the present, from the first atoms to consciousness, from Earth to the edge of the observable universe, and now, gently, softly, peacefully, you can let it all go. Let the facts fade, let the numbers dissolve, let the cosmos grow quiet. There's only this moment, this breath, this gentle descent into perfect rest, into perfect darkness, into perfect peace. Thank you for journeying through the cosmos with me tonight, for learning these 100 facts about space, for wondering with me about our place among the stars, for staying until the end, or for drifting away whenever sleep called you. Either way, you're exactly where you need to be. May your sleep be as deep as space, as peaceful as the void between stars, as timeless as the universe itself. Good night, traveler, rest well, among the stars, in the gentle darkness, where all journeys end, and all peace begins.